Okay, so let's continue on basic examples of generating function. So let me state another problem. By the one question, so are you finding, so we are posting videos and handwritten notes, both the class notes. Is it like most of you finding it useful, or only handwritten note you think for discrete math is enough, or you need videos? Like, are you watching any of you these videos offline? It helps.
Yes, sir. Videos are
Better.
especially for me is very helpful. Especially for the graph theory part, I was watching them again, so understand it better.
Okay, so people are finding it helpful. Then we'll continue posting videos as well as the notes. The note sometimes problem is that it becomes too big, and Moodle sometimes it doesn't support. That's the problem. Okay, so let me state a problem. Find.
So in that case, you can upload in a Google Drive folder and share the link.
Yeah, it is possible, but what happens? I want to keep everything in the Moodle basically. Otherwise, it becomes an administrative problem later.
You can share the drive. You can share the drive link on the Moodle.
That's possible, but since there is an administrative issues that I don't want to discuss here. So, but it's better to keep if we can on the Moodle. But Moodle is allowing 8 MB, so sometime maybe we have to compress and fit it into that. Okay, so let's see. So let's look at this following problem. Find the number of ways to split an end-day semester into 3 parts. So we were learning this product rule of the generating function, right? So this question is motivated by that, such that any number of holidays in the first part odd number of holidays in the second part and even number of holidays in third part. Okay, so this is the problem. So there is a semester which is running over n days, and we have to break up the semester in 3 parts any way you want, such that in the first part you can allow any number of holidays. Okay, and in the second part you are allowed to use only odd number of holidays, and in the third part you are allowed to use even number of holidays, and you have to find how many ways you can have this arrangement. Okay, so
we can place holidays whenever.
1 minute. Hint: use I'm coming back to someone started saying use product rule of generating function. Yes, Rami, tell me.
So the holidays are predefined, or we can place them in.
Holidays are?
I mean, are the holidays given to us, or we can place the holidays on whichever
No, you
day?
can place and do whatever you want. Any number of holidays you can choose. You have to only satisfy this constraint. For example, the second part, you can only choose exactly odd number of holidays. And the third part, you can choose even number of holidays, but any even number or any odd number in that spirit. And the first part, you can give any holidays. It could be no holiday, or it could be any odd holiday, odd number of holidays. It could be any even number of holidays, and so on.
In how many parts do we have to split it?
Three parts. Yeah. Think about the problem, and if someone comes up with an idea, it will be good. Probably, I think one should mention here that some part can be empty also. Like it's really like at most 3 in some sense. Some part could be trivial. It could be like 0 part. I hope that's the meaning of this problem from the source. Okay, so we can think in a different way, like maybe in a purely combinatorial way also one can think, but let us discuss a more systematic way to approach this problem. So what is the idea in this kind of questions? Idea is set up 3 generating functions for 3 cases. So there are 3 cases, right? The first could contribute any number of holidays, the second should contribute odd number, and the third is even number. So these are the 3 different situations, and we want to construct 3 generating functions for these 3 cases. And then naturally what you will take is a product, right? Now if you take the product of this generating function and collect the total power of x power n, that should give you all the possible arrangement, right? Then you are satisfying the condition 1, condition 2, and condition 3, because they are coming from the respective part of the generating functions. This is the main idea. Is there something in the chat? No, it is regarding the book. Okay, so let's see how. So with this hint, can someone come up with an idea? How shall we approach this problem? So let's try to write a generating function for the the first chunk. So this is the 3 part you have broken the semester, right? First, second, and third. So let's try to find a generating function for the first term. Remember that in the first term, you can allow any number of holidays.
So 1 plus x square plus dot dot dot, or 1 by 1 minus x.
Why is that? Because what is the meaning of the generating function? That x power n, the coefficient of x power n should determine the number of ways you can give holidays.
Yes, so
So the
first
example that you said, it means like number of ways you can give holidays is 1. So that's not correct, right?
no, so the first part, right? You asked.
Yeah, I think this answer is in the chat. So it's like 2 power k x power k. Essentially, all possible subset of n you can allow like holidays. I don't know that you meant to say that.
So like parts could be like, they don't need to be contiguous, is it?
They are contiguous, but the first part could be any numbers.
Like the first k days, is it not like that? Or like it could be any k
Yes,
of the k
but
days?
that k could be like, why this 2 power k? Because okay, 1 minute. Let me see what he wrote in the chat. So Subramanian, do you mean that is a summation over all k? This is the generating function you are proposing? Yeah. So, okay, someone asked a question. So here the idea is that you can allow like any number of holidays in the fast term. So let us think about it. So who asked that contiguous? Someone asked something about contiguous. Let's get back to that. Who asked? Who asked? Yeah, this I think the person who wrote, I'm just trying to make it interactive, that 2 power k x power k Subrolin. I think what he means is that if you allot the k days, for example, let's say for your first half, then among these k days, any possible 2 power k choices could be holidays. I think that's his interpretation. Is that the interpretation, Subranil, you had in mind? Right. So, and someone asked about some contiguousness. I hope this answers your doubt.
So I have a doubt too, sir. So, for example, in the first part of the semester, are we just concerned about the number of holidays, or are we also concerned about when exactly the holidays are?
We are not concerned about when exactly the holidays are. That's why he chose any subset of k.
So just one number will be enough for the first.
Right.
So, am I right?
Right. So suppose the first half is over k days. That's the Subramanian solutions. First half is over k days. Those among first k days. Okay. Just the picture I drew. Among the k, you could place your holidays in any subset of k. That's the reason the 2 power k stands for. Is it clear? Apratim, what is your name? Apratim. Who asked? I don't know.
I asked, sir. Apratim or Apratim, it's fine.
Yeah.
I didn't quite understand though. Like, let's say there is k days, and
suppose the first has k days, right? I'm just using his notation, so Brunen's notation. So among the k days, you can allow any number of holidays anywhere. So that means you can choose any subset of these k days and mark, oh, these are my holidays.
Right, I understand.
Right. So that's the solution he gave when he wrote it is like 2 power k into x power k. Subramanian, I will continue to use n, so I will not write k because k may get mixed up with something else in the note. So I write the generating function as 2 power n x power. Is it correct? Now you, okay, so let's write the generating function for the second thing, the first, This is the first case. Now let's write generating function. And the second case. Can somebody point out the generating function for the second case?
2 to the power n minus 1 into x to the power n.
Very good. Right. So let me call it bx. Because you see, so second half, you have only odd number of possibilities, right? So if you take, if the second, if you take like k days here, then you have k choose 1 plus k choose 3 plus k choose 5, this sum, right? And we know that this sum is up to exactly half, 2 power k minus 1. So as he correctly said, the generating function for the second case is 2 power. These things are really fun. I mean, if you think it properly. This is for the odd case. So let's say generating function for the third. This is, someone else can say, this is exactly like second with a just, you have to be careful, right?
Starting from 0. No, not 0.
Right. I think someone already pointed out. What is, Rishabh, what is your, I don't understand your notation. I understand your idea is probably correct. So bx times, can you just explain your notation? I don't understand. Bx times
bx we wrote in the second case plus 1 plus.
Okay, good. So as Vijayan also said, that the generating function for the third case. So if you have a 0, that's also a possibility. That's a vacuous condition. Cx is 1 plus bx basically. That is, this 1 is for the n equal to 0 case and n greater than equal to 1 case. So these are the generating function. Good. Now once we have this, our life becomes very simple. So the final generating function
Product of these three.
yes, that's the advantage. Yeah. So you see, the advantage is that after that, the game really becomes mechanical. We don't need to think math. It's just a calculation, right? So let's write that final generating function fx x bx cx. Now let's substitute closed form for ax. What is a closed form for ax? Ax is, you people must be much better than me because you are fresh in doing these things.
1 by 1 minus 2x.
Say it again.
1 by 1 minus 2x.
1 by 1 minus 2x, right? Just substitute 1 by 1 minus 2x. Yes, you would be much faster than me in doing these things. So what is bx? 2 power n minus 1 times x power n greater than or equal to 1. So this is, first one was very easy. It's just a geometric series, right? What is the second one?
Half into a minus 1. No, a minus 1 into half.
Bit slow again. Vijayan again.
Like 1 by 1 minus 2x minus 1 into half. Like,
I don't know.
It's just
So okay,
ax by 2.
you have to derive once. Yeah, that's the correct answer. X by 1 minus 2x. You have to differentiate. No, you don't even differentiate. Just to take x common, right? X. So that's what you probably mean. Yeah. So this is very simple. So right, you don't need to even differentiate. And what is cx? Cx also the same thing, right? X by 1 minus 2x. Yeah, this was really simple. Okay, so now let's write fx step by step. So fx is 1 over 2x, x by 1 over. Now what shall we do? What I want to find? I want to find the power of x power n. That's the coefficient I'm looking for my solution. So how shall I approach that from here? Anybody? Again, some 10+2 trick we will use, right? What the trick could be? It's a product. We don't like a big product. Rather, we will like a sum. There, because sum we understand very easily. So how to go from this product structure to a sum structure?
So we
So,
can use the binomial theorem.
for example, the x by 1 minus 2x, the x on the top, we can add and subtract half.
Yes. So
Then we can split it into two sums.
So let me just write it in a slightly neat form so that you can understand. But this should remind us some technique that we have learned, let's say in our class 10+2. How to write it. The technique has a name, right? Can you remember the name?
Partial fraction method.
Exactly, partial fraction method. So we'll do that. Can someone tell what shall I do for partial fraction from here? Just using our 10+2 knowledge.
A by 1 minus 2x plus B by.
Right. Square, right? So that is equal to x. Now we can clear up the denominator.
So instead of b, shouldn't it be something like bx plus c?
D, what is D?
No, sir. Instead of b, you just wrote b by 1 minus x the whole squared. Shouldn't it be bx plus c? Because b can be a linear function also.
But you
Instead of
can
a constant.
eventually make it like this form. If it is a linear function, you can again split it by subtracting and adding and bring it to this form. If you want, you can put a, sorry, I missed. You can put a scalar term here, right? So there are 4 terms, A, B, C, D, right? So now it's simple. I will not do the full calculation. I think you can guess what I am doing. So you just write this thing. These calculations I won't do, then it will be very boring. And then you substitute the value of x and solve for it. If you solve for it, what you will see that your fx, this you can solve as a higher secondary exercise. I'm not going to do it. So fx will look like 1 minus 2x. Yeah, this linear form that you said, it can be further broken into these pieces. So I just step jumped and wrote it directly like this. I hope it's clear. And then, so this is a very nice form I got, right? The sum of 2 terms. Now I can extract the Fn. How shall I extract? What is the nth power coming from the first one? That's very simple. So this is 1/4 to power n. And what's coming from the second term? So that's my goal, right? So I know that 1 minus 2x power minus 3. What is the coefficient of x power n here? That is 3, 3 plus 1, 3 plus, this is binomial coefficient, expansion with negative coefficient, right? Factorial n, which is n plus 2 choose 2. So this is 2 power minus 1/4 plus 1/4 n plus 2 choose 2.
There will be an extra power of 2 power.
There is a 2 power n right here. Correct. So this is these calculations are it's not very interesting. You can do it, but the conceptual part is that how do you construct the generating function? That's the key. So these calculations we can do, maybe you can do it much faster than I do because you have just done it 1 year back. But that's not the point. Point is that how do you attack such a problem, right? So that we have to be careful. Okay, so let's go ahead and continue with further examples. Partitions. So we already introduced partitions, and that time we discussed like partitions have a special role to play in combinatorics, and often these partitions are the problem involving partitions. We sometimes, many times, in fact, we do not have a nice closed form, but still people wants to estimate, and this won't be covered by this course, but you will see there's this partition problem involving partition has some very nice relation with the problem involving generating functions that we'll illustrate now. So let's take the first problem. So let's P less than Kn. This symbol means the number of ways of partition in into parts of size at most k. What do I mean by that? You have to write in maybe A1 plus A2 plus AT, where T could be anything, but the AIs could be at most k. You cannot use the values more than k. You can use any number of them if you want, but any value should be bounded by k. Right? And the generating function associated with this problem is the following. So we want some kind of algebraic expression for this generating function. This is like a very symbolic, right? I do not know about these values, but I want to express this as a identity that is equal to some nice algebraic form. This is very symbolic, right? I have not told you what is the value of pkn. I just wrote it from the definition that this is the generating function for this function. But I want a nice identity.
As a product of polynomials, so isn't it just like 1 plus x square into 1 plus x square plus x?
Yes, you are right. It is
A generating function. Generating functions, I mean. And till 1 plus x k, x to k, and so on.
Your solution is correct. Let me just explain to the people who are thinking it for the first time. So, what are the things that you can use in your collections? You can use 1, you can use 2, you can use up to k, right? And what is the idea? That 1 you can use any number of time, so as 2, so as k. Of course, when I say any number means you should not exceed the n, because that's there is no negation is allowed here. You are partitioning n. But you can use any number as long as you are within that limit. Okay, so now let's translate the first part, that you can use any number of 1 in your disposition. For that, I write the generating function 1x, a1x. That is exactly what he said. 1 plus x square. I'll take the infinite series because it will not matter. But this side also have an infinite series, and coefficient by coefficient it will match. But what is the meaning of this generating function? The first term means you have not used the number 1. The second term means you have used the number 1 once. The third term means you have used the number 1 twice, and so on. Similarly, you can define a2x 1 plus x squared plus x power 4 and so on. That means you may not have used 2, the first term, that's sorry, x2 power 0. You have used 2 only once. That's the reason x squared comes. You have used 2 twice. So that's the reason x power 4 comes and so on. And finally, akx 1 power xk. The same argument, right? That a kth part you have used 1 or never or twice and so on. So now, this identity that you are looking for is really product of this generating function. Because the reason is very simple, right? Any x power n coefficient that you come or you rather count from this side will contribute 1 to your valid partition. So this is equal to 1 by 1 minus x, 1 by 1 minus x squared. So that is what I think Rohan said.
Yes,
So
sir.
so this is what I mean by a nice algebraic form. We can see it in front of us. Okay, so let's modify the problem a little bit. We no need to do it, it will be immediate. So let's remove this less than equal to case things and just write Pn x power n. So what will be the identity for it? So let's write it product of what will be the identity for it? There is no bound. You can use anything that you want. So obviously by the same argument, you can have an infinite product.
How do we prove the convolution will converge in that x power nth coefficient? That convolution will converge. That will be finite. That should be finite.
That should be finite because if you have x power n, let's say, and when you have this an, that an start with 1 plus x power n, x power 2n. Sorry, what is your question? I didn't get your question. What do you want to say?
Here we are having an infinite product. So in the convolution, which is the x power n coefficient, that will have an infinite sum. So how to prove that will converge? We know the power series are sums of infinite sequences, but here we are having infinite products of.
No. This is like at most you can use n, right? So it will never have anything in its count which is more than n. So it will be always finite.
Pn isn't from the right hand side, the coefficient of x power n, won't that be an infinite sum of
that is
sum
okay.
in the convolution?
That sum always converges because this Pn, nothing is allowed more than n. Because it's a partition of n. It's a partition of n. So nothing is allowed like which is more than n. So that's a finite collection.
So in the first problem, is t fixed, the number of summons?
Number of summons, you mean how many is that t? This t?
Yes.
No, t is not. T could be anything.
Okay.
I mean, this is by the definition, there is no divergence issues because pkn is a finite quantity. You cannot use more than n in the summation.
No, pkn I understood, but pn, the second question, we are considering the infinite.
What is the infinite sum that will come here?
The convolution sum, the x power n
That
term.
is okay, but look at how x power n is generated here.
Okay. So yes. Only finite
That is
number of
infinite, but
sequences will contribute. Yes.
but that summation will be finite.
Yeah.
The T confusion is clear. Who asked? I think someone. Who asked that?
Yes. So
Saptarshi. Is it clear, Saptarshi? The T is anything that I am using here?
yes. T is,
See,
so
my argument there is T is not playing any role. Of course, by this argument, T is at most n, but it is not directly playing any role in my argument. Can you see that? See, I have used any number of ones, any number of twos, right? So it is covering in some sense any
yes,
possible
okay,
T that you can look for.
Yes. Okay.
These things are a bit tricky when you see it on the first time.
Sir,
Yes.
Vijayan asked a question. Could you repeat what he said about only finitely many contribute?
Oh yeah, he said this is like an infinite product. How do you argue that this is an identity? I mean, how the convergence is happening and so. Right? Why this is true? That summation of p and x power n equal to an infinite product. That was his question. So he is thinking like this infinite way it can come and then it may not converge. Something like that. Vijayan, was that your doubt, right?
Yeah, the convolution sum we are getting that, but only finitely many terms will be contributing.
Right. Yeah. That's the reason you don't have any problem.
Oh, so we restrict K to N. I mean,
Yes, because n, I mean, you cannot have a negative partition, right? If you go further, there is no way to balance it out. So you can at most take a number which is n. It's not more than that.
Okay, so that's why there are only finitely many contributions.
That's why this doesn't. But this is a point which is of considerable importance, and that will crop up in some place in future. You will see that we will handle a place more carefully. Okay, so good. So problem 3. Problem 3 is this number. PDN. PDN means number of ways partitioning n into odd parts. Odd part means all the component that you are using, they are odd numbers. For example, in the partition of n, you are not supposed to use 2. All you can use 1, you can use 3, you can use 5, these numbers, so odd numbers. And we want to compute this algebraic expression for this. So let's do that. It's very simple, using just the analogy of the first part. Someone should try it. People who know or seen it already, they should not say it. People who are seeing it for the first time, good for them to try it. It's very simple, right? The first problem, you are allowed to use everything. 1 any number of times, 2 any number of times, k any number of times, and so on. Here you are supposed to use 1 any number of times, 3 any number of times, 5 any number of times. So what should be your generating function?
1 plus x cubed plus x power 5 plus x power 7.
Not, you can start from x squared. I mean, include 1 and then you can include the cube term, right? Because 1 could also be included.
Yes.
So that's like product I sort. Actually, I should use odd. By mistake, I wrote this is O for odd. And problem 4 is actually this is D. PT. Repeat is again the same problem, the distinct part. No number you can use more than one. You may not use it, but no number you can use more than one. So what's the generating function for it? That's not equal.
Repeating terms we can omit. I mean 1 plus x, then 1 plus x cube.
Yeah, why did you leave 1 plus x square? 1 plus x square
because oh yeah, of course, 1 plus x.
It is everything. This is not odd.
Yes.
But you are on the right track. So you can already sense that one can manufacture like different question here, right? Like odd numbers, I can say that you may not be able to use more than one. Even you can any number of all such questions can be manufactured. And if you learn this trick, how these crazy series are coming, then you can solve almost anything here. That's the fun of doing generating function. Okay, so good. Right. So after all these simple things, let's move it to something a little bit complicated. Any doubt or any problem you are facing? So here is some advanced problem. So just a moment. Okay, so here is a classroom. And there is an empty jar here. Okay. And there is a student. The student, he enters in the classroom. Either he can place 1 rupee into the jar, or he can take out 1 rupee from the jar. Okay, that's the only thing he can do. Student, this was initially empty. Student can, on each day, student can either put 1 coin or can take out 1 coin from the jar. Yeah. Okay. So now Cn is the number of ways the jar is empty on 2 nth days. That means there are day 1, day 2, day 3, and day 2n. And every day the student enters in the classroom, and from the jar either put 1 coin or takes out 1 coin. And the condition is that at the end of the 2n day, the jar should be empty. How many ways this can happen? That's the question. So symbolically, when a student put something in the jar, I will assign it to +1. Let's use a different color maybe. So when he put something in the jar, I will put +1, and when he takes out something in the jar, I will put it in -1. So the action of the student, is a sequence of +1 and -1. Is the problem is clear? Yeah. So the question is how many ways these things can happen. So I
So
just
we did this in probability theory as well.
Oh, okay. So if you have seen it, then you don't say the solution. Which probability in some course in CMI?
So in our second semester course, probability.
Is the first semester there is a compulsory course on probability, is it?
Second semester, this semester only, sir.
It's a compulsory course on probability?
Yes, sir.
Who is teaching the course?
Professor Shankaran.
Professor?
Shankaran.
Shankaran, okay. You have seen this problem in the same language?
In similar language, quite similar.
So let me just give the initial condition. Then you people already know it, but it's good to, because it's very important in combinatorics also. So he is covering the finite probability also, finite probability space, not just continuous thing. Like discrete probability also is covering, right?
Yes, sir. Yes, sir.
So then there will be a big overlap with our probability and that probability. I should check it. This is BSc which semester going? Your third semester, right?
Second, sir.
Second semester. Is this some elective course of probability, or they have made it compulsory? Full course on probability is compulsory in BSc second semester.
Yes, sir. It's a core course for all students.
Oh, I didn't know that. Okay, so if somebody doesn't remember it from probability class or seeing it for the first time, you should try it. Or I assume that everybody knows it, then I'll ask someone randomly.
Will it be 2 NCN? 2 NCN? 2 NCN?
Yeah, don't give the answer. Just tell me the approach. How do you attack such a problem? Because I know this answer.
Here we have +1, -1. It sums to n. So we just permute them. Like number of permutation gives one corresponds to the number of ways that can happen.
But that is not correct, right? Because in that case, you can, for example, start with a -1, or you can run into the trouble that jar has become negative, which has no meaning.
Yes.
The simple permutation will not work.
Sir, the constant term in x plus 1 by x raised to n.
Can you just tell it again? Constant term?
In x plus 1 by x raised to 2n.
Are you trying to construct a generating function for it directly?
Yes.
But what is your idea?
Like we can either put in a coin or take in a coin. So
right.
Sir,
but generating function, you can, 1 minute just to answer you. So you are using -1 in the exponent. These kind of ideas are not going to work, because these are not, I mean, you will end up in rational expression and things like that.
okay.
Yeah. Yeah. Someone started saying yes. Saptoshi, yes, you started saying something.
Okay, I've done something. I think it's wrong anyway. Okay, so
but all of
1
you
plus
have done
x.
probability, then it's not interesting for you.
Uh-huh.
All of you have done probability class.
Actually, I don't remember doing this.
So we did the reflection proof, like the combinatorial interpretation, reflection proof.
Okay, so let's me just give you some hint, and if Roshan, if you know the solution, don't give it. Let's other people.
Sir, actually, we haven't exactly done this problem. We did the answer we'll be able to understand, but I mean, many people haven't yet made the connection which Rohan has made.
I see. Okay, so this problem, this number that finally comes out is a famous number. This number is called Catalan number. I think already probably some of you know. Cn has a famous name in combinatorics, and this number could appear in variety of problems. So this is one of the harder instances of the problem, but it can appear in many other problems, this Catalan number. We'll see in future. So this is a famous number in combinatorics. Okay, so let's not worry so much about the number. Let's try to see how we approach such a problem. There could be multiple ways to approach this problem. We'll do one way. Okay, so the what is the condition? That jar should be empty on 2n empty. That means if I take this +1 -1 sequence, I'm thinking like this: b1, b2, bn, b2n. So these bi's could be either +1 or could be -1. Okay, so what do I want? That jar should be empty. That means if you add all these numbers, you should get a 0. But that's not enough. Then the problem in Vijayan's approach that I pointed out, that puts a constraint in this problem. What is a constraint? That jar can never become negative. That is meaningless, right?
So sum should be positive. Greater than
right. So constraint is that summation of dj j equal to 1 to k, where k is, let's say, bound less than 2n. This quantity can never be negative. So this is a condition you must satisfy. And yet you have to prove that, you have to count that number. Yeah. Okay, so one minor observation is that I just, if you want, you can verify it offline, that jar can be empty only on even number of days. This you can, if you want, you can. It's kind of obvious. If you want, you can verify it offline. So with that in mind, so let's put the picture. So this is the day 1 and this is the day 2, right? Right. And let's say 2i is the some day in between where the jar becomes empty for the first time. Okay, so let's before we go ahead, let's just give this sequence a name. It will be useful for us. So these are the sequence of the type b1, b2, b2n, such that any prefix is non-negative. So let's call this sequence, this type of sequence, let's give it a simple name. Let's call it good sequence. And so 2i is the first day where the jar becomes empty. Okay, right. So now look at this part of the action. So this is like 2 into n minus I days, right? So this time the jar becomes 0, and this time also jar becomes 0. So all these things that you see here, they are like good sequence. So what plus minus 1 values you are placing in 2 into n minus 1 I days, they corresponds to good sequence. We agree on that? That is kind of obvious, right? Here it becomes 0, and then you start again putting things and taking out things, and 2n times it becomes again 0. So you have basically you have gone back to the your original problem itself, just shifting origin from 1 to 2i. There is no change happened. So here this corresponds to good sequences. Any doubt on this argument? Any sequence that is placed between 2i to 2n is a good sequence. Right? And now look at the sequence 1 to 2i. This is also a good sequence, but with a little bit more constraint. What is the constraint?
So it necessarily starts with the 1. Oh, but that is the same for the next part also.
Yeah, that's same for the next. This is like it's keeping like empty jar in the school day and school room, right? That's not the constant, but there is a more important constant.
It cannot become 0 at any point.
Say it again, Romit, louder.
So the sum cannot become 0 at any point.
Exactly, that's the constant. So no prefix sum can become 0 because you, by your choice, you assume that 2i is the first such number on which the can becomes empty. Just give me a moment, right? I need to switch on my light. So these are also good sequences. With an additional constraint that summation of bj j equal to 1 to k is strictly more than 0 for all k less than 2i. No prefix can become 0. It's clear. So let me give these sequences also a name. Like the earlier sequence, I gave them good sequence. So let's call this type of sequence very good sequence. Okay, so what shall I do after that? Now observe that in this first part 1 to 2i, which is like a very good sequence, the sequence starts with +1. You have to put something in the jar, and then at the 2i thing, jar becomes empty. So you have taken out something. So this is like ends with -1, right? So the first position is fixed to be +1, and the final position is fixed to be -1. And the remaining things, this is like 2i minus 2 positions. What can you say about these sequences?
It's a good sequence.
It's a good sequence, but is it a very good sequence?
Not necessarily, I think. We can touch one again, but we can't.
Not precisely, not necessarily, because you have taken out +1, right? That's not in the sum anymore. So it may be 0 also. So this is good point. So this is corresponds to good sequences. Only this part. But this is like 2 into I minus 2. So, and by our notation, Cn denotes the number of good sequences on 2n days. So, and this is like 2i minus 2 days. So this number is Ci minus 1.
Hello, sir.
Yes.
Sir, I did not understand why this part is good sequence. I mean, we have one coin at the very first place, and after that we can either take it away or put another. So how does that start with a 0 necessarily?
But that's not the definition of the good sequence. Good sequence is defined like the action of +1 -1 where no prefix is negative.
Oh, okay, sir. Okay.
That's not a problem. Okay, right. So now what shall we do? We have all these bits and pieces of the information. Now, what are you actually? Why did you break it the problem like this? All you had, so this part 2i to 2n, we know that these are like again a recursive call of our problem. These are like good sequence, and this is like very good sequence. So intuitively, we are trying to compute, a generating function for very good sequence and a generating function of the good sequence and multiply. Because these two parts are happening independently, right? Then you want to multiply. You agree with me? So the generating function for the very good sequence, let's try to understand. In the argument of very good sequence, what we did, the first bit and the last bit are frozen to +1 and -1, and inside things are the good sequences. So this was like 2i, which is determined by 2i - 2. That means if you take this to be like 2n, it will be determined by 2n - 2, which is cn - 1. That's the reason this generating function is cn - 1 x power n. You understand the logic? But this is by the definition, we want to compute that our target generating function is cx, that is summation of cn x power n. In fact, let me, yeah, that's right, cn x power n. And this starts from cn - 1 x power n. So this is exactly x times cx. 1x is additional. That's good. And this part is very easy. We already know that this is like good sequence. So generating function is cx. So if you combine these two parts, very good sequence and good sequence, the total generating function is a product. Which is xcx times cx. And that's intuitively our generating function that we are looking for. But there is a little catch because of the boundary condition. What is that catch? The catch is that for n equal to 0, this argument of partitioning does not apply. So you have to exclude that n equal to 0 case, and this is equal to the other things of the generating function. In particular, this is equal to cx - 1. If for n equal to 0, this kind of partition business is not applicable. So that boundary condition we just subtracted from the cx and wrote it cx - 1. So this is really funny, right? This product of this quadratic expression is equal to, in fact, cx - 1. So this gives us nice handle. So this gives like cx square x minus cx plus 1 equal to 0. This is like solving a quadratic equation. That gives you a nice form for cx. Cx is minus b, that is plus this minus 4ac by 2. Yeah.
Sir, could you once explain the boundary case, how we get
Yes.
x minus 1?
See, if n equal to 0, then this kind of analysis is not applicable, right? Because I have taken like the first time this 2i where it got 0 and then separated out the next part. If you start from n equal to 0, that's like a vacuous condition. There is no such breakup and do this kind of product analysis. So I just excluded that boundary condition. See, this
So
has
in the
always,
LI case, this n equal to 0 case is considered. That's why we are subtracting from the RHS.
exactly, because this thing, you see, everything comes up with the additional product of x. But in the generating function, there is one constant term also that has no x. And that is commentarily because of that reason, that n equal to 0, this kind of breakup rule is not meaningful. So we just deleted that part of the boundary condition and rest are same.
Root over 1 minus 4x by that means that expanding it in summation form.
Correct.
That is the process for that.
Correct. We will expand it. This you can check. I will not. I mean, this is like your higher secondary binomial expansion with the fractional coefficient. So if you expand, it will look like this. Just your 10+2 knowledge. There's nothing extraordinary in it. So this is the expression of thing. So that means Cx, if you plug, so which one you will take, plus or minus? Which solution you will take?
Yes. Oh, no. One which will give positive
plus will not have any meaning, right? There are a lot of negatives. So you should take the negative. So 1 will go up. So this will be like 2x plus greater than or equal to 2. So this is like 1. I guess make any mistake of any 2 in this part. Will there be 1, 2 also here? Anybody can quickly remember this expansion of this binomial thing, or you can do it in your notebook. I guess there will be 2 here. It is not just this, there will be also 2. So that 2 should get cancelled. So you got 1. So that 2 will get cancelled. So there will be 2 here. So this will be like 2n minus 2, n minus 1 by n times x power n minus 1. So the Cn, which is like coefficient of x power n, you basically have to substitute n by n plus 1. Then you get that coefficient of x power n. So that will give you 2n choose n by n plus 1. This is called the famous Catalan number. You will see that Catalan number has a lot of combinatorial interpretation. We will see a few examples later. It can appear in many places in different ways. So now tell me, is that the thing covered in? So probability, I think probably the question they turned into a probability, like what is the probability that this will be a good sequence or something like that, right? That was probably the question.
Here we consider those lattice paths. So, method of representation.
Lattice
paths. lattice points, and then consider diffraction.
Maybe some of you can share the what is the exactly the probability syllabus. Then we will understand like how much or what level it intersect with our probability, and then we may skip. If all of you are comfortable with discrete probability, then we can skip some part and teach something else there. So maybe one of you should share the syllabus. Is the course is currently running or it's over, right? Course.
No,
No,
sir, it's running.
Okay, so can someone quickly point out that what are the things? Maybe I stop the recording. I think this is fine. Though already 6:50.